Hello guys, how are you? I hope you are good. And today we are going to talk about reactions of aromatic compounds. As everybody knows, the aromatic compound generally gives the electrophilic reactions. So in the electrophilic reactions, the uranium ion mechanism you will see in this type of reactions. Orientation and reactivity energy profile diagram that we see in this lecture and ortho, para, or ipso attacks orientation in other rising ring systems. You know, it depends on the group that those were attached to the ring. So as there were any ring, there is any group attached to the ring, then it will decide the next coming group or upcoming group where it will attack. Okay, so the quantitative treatment of the reactivity in substrate and electrophiles that we will discuss over here. Other thing we understand the diazonium coupling. Diazonium coupling is type of like this, and one of benzene ring is here, and one of benzene ring is here. So you will understand it is used for the formation of dyes. So you will also understand this thing. And the Bills-Mayer reaction, it is also very important on by the point of view of the examinations. Guttman and Koch reactions, actually it is also important reaction, and you study these reactions in 12th standard especially. We are going for the next page. It is electrophilic aromatic substitutions. Both benzene alkene are susceptible to electrophile. This is defining electrophile, and the positive charge on it defining it has the positive charge. Lack of electron. Attack due to their exposed pi electrons. Their exposed pi electrons. The available pair of electrons, they attack on that pair of electrons. So this thing gonna attack on this. Here you can see the cyclic compounds, like this is a benzene ring. This is benzene ring. This is a cyclic benzene ring plane itself. Every p orbital overlap with two neighboring p orbitals. Every p orbitals overlap with two neighboring orbitals. It is like that. Okay, the double bond you will notice over here. Neighboring p orbitals bonding in ethylene. Over here there is ethylene. So you can notice over here there is one of the single bond over here, and this is pi bond right here. Okay, this is a pi bond. The two of the orbitals like this was share their bonds with each other. It is called the pi bond. It is called the pi bond. Okay, we go further. Electrophilic addition in alkenes. Normally, when you notice all the unsaturated compounds, most of the times give electrophilic reactions, and with that, the special thing they gives additions reactions. So here you will notice like this is one of electrophile. The electron pair is shifting toward this, so there will be the positive charge and there would be negative charge because the electron pair is going to this side, upper side. So as these electrophiles comes and attack on negative charge, and this bond is formed. So before it was sp2, and now it turned into sp3. Keep this thing, remember. Okay, then the left charge, this it is become the cation, and this is a nucleophile, and it attacks over here, and this molecule is formed, and this is called the addition compound. Okay, now it is becomes cycloalkane. Why electrophilic attack in benzene? Why? What is the reason only electrophilic attacks were takes place most of the time in benzenes? So you will understand the high electron density of the ring. High electron density of the ring makes it open to attack by electrophiles. As you know, in the case of the benzene ring, you will notice like benzene ring looks like this, okay, and it has like the electrons remain delocalizing from one place to other, and the double bond remains shifted from one place to other, like a one carbon to other carbon, the electrons remain shifting. So just because of this, every carbon has like this carbon, these the six carbon over here present here six carbon, and the six of the carbon has the same amount of the electrons. So we can say like the amount of the electron distributed on carbon is remained constant. So in this case, what's gonna happen? The electrons were attacked by nucleophile. Instead of nucleophile, they were attacked by the electrophile easily. So to keeping this thing in the mind, we can see like the benzene is attacked by nucleophile, electrophile, I'm sorry, electrophile instead of nucleophile. And further we go, the second thing, however, because the mechanism involved an initial disruptions to the ring, electrophiles will have to be more powerful. This is the most important thing that you have to keep in your mind. The electrophile must be powerful. The most powerful things like if you have something like ClBr will not directly attack on any kind of the benzoating, not directly attack. Okay, you have to keep this thing in your mind. It takes the help of some other Lewis acids or some kind of mechanism involve an initial disruptions to the ring. Electrophiles will have to be more powerful. The electrophile, the species that we are talking about, the electrophile must be powerful. Like it must be powerful, not weak electrophiles. Then those which react with alkenes. Then those even the easily any of the electrophile can attack on alkenes. Any of the electrophile can attack on alkene, but to attack at benzene ring there must be a powerful, like we can say like the alkene can be attacked by HCl, can be attacked by Br. So these is a very simple we call it like a weak electrophile, so it can attack on benzene alkene but not on benzene. So you have to keep this thing in your mind. Okay, the next thing we understand, the a fully delocalized ring. Delocalized mean like there is a benzene ring and like this, and here the electron remain like it will shift to this, it will shift to this, it will shift to this. So like that the pairing becomes like that. So it's called the resonance structures of the benzene ring. We have to keep this thing in your mind, and this is called the delocalization from one carbon to other carbon to other. Okay, so here what is happen, like these electron again shifted toward these, and the electrophile will attack on the negative charge once again, and that's we see over here the nucleophile will attack over here, and the reaction becomes like that. Okay, but remember, does not form this product since less stable than starting material due to loss of aromaticity. So what we say that most of the aromatic compounds, all of the aromatic compounds are more stable as compared to other general aliphatic or cyclic rings. So you have to understand over here the concept, like to be stable they will not be stable like that. They have to go a process to retain their aromaticity that we discuss other area of the life. Okay, here. Ben Therefore, benzene undergoes substitution reaction rather than the addition reaction. As we see before, saw a reaction that was alkene. The alkene was giving addition reaction, but over here benzene gives substitution reaction. So you have to keep this thing in your mind too. So over here, what's gonna happen? Like this is one of sorry, okay, Arenium ion, its mechanism Se2 reaction. The electrophilic substitution. It is called electrophilic. The, my style is not working properly. Electrophilic substitution reaction. So these things will attack and these will form. And now it is become aromatic once again. So this is called the product of these. So in this case, what can happen? In the presence of catalyst, the nucleophile is attracted by catalyst and the electrophile is formed and the nucleophile is formed. The next step, what can happen? In the first step, the electrophile will come and attack on it like this. Slow reaction determining step. RDS mean reaction determining step. So the bond shifted toward these, they have changed a little bit, and then the hydrogen bonds breaks, and what we see, the once again the bond is retained over there, and this condition is known as rhenium ion. We land intermediate or sigma complex. The carbocation sp3 hybridization due to new sigma bond electrophile bonded electrophile. Although Wayland intermediate is stabilized by resonance. It could be stabilized by resonance. So over here what we see, there is a positive charge. So it's shifted here and the positive charge comes over here, and then these bonds shifted here and the positive charge over here, and then what we see, it is rotating from one place to other, and in that time the bond of these shifted here and the hydride ion removed. This is called hydrogen ion is removed, and the aromatic compound is formed in the end. We have clearly lost the aromatic stabilization of the starting material, and hence the addition of the electrophile is going to slow step. This is called RDS, rate determining steps, that we can calculate the rate of the reaction by this step according to the chemical kinetics. Okay, and now the second step will be fast, because why it is fast? To retain its aromaticity, it will lose one of proton and retain its aromaticity. So over here what you see, like to retain its aromaticity, one of nucleophile can take this proton away and the bond is shifted, pair of bonds is shifted over here, and a compound is formed, and this compound is called substituted compound of the reaction. We go further. Here we see the energy profile diagram of uranium ion. Okay, so over here, this is the main compound attacked by nucleo electrophile. Oh, I'm sorry, it's a not nucleophile, it's electrophile, and this electrophile then it comes into the stage of transition stage. Transition state, the a transition state is known as like the a point where the bond breaking of the bond and bonding and a breaking of the bond will taking place together. Okay, so over here then it comes into the stage there, it is called the intermediate, like the bond is formed and the ring is stabilizing the charge, and then you once again go to into the reprocess, and the proton is abstracted by the nucleophile, and then it come back and it is called as the product. So the first E activation energy of the first step is greater than the second step, that you can see over here. There is a difference between the energies. So this is the E1, we call this E1, and this is called the E2. Got it? Next thing we discuss over here, the halogenation of benzene, the need for a catalyst. We will discuss about this later. And thank you very much for being stay tuned with the lecture. And I just say, okay, please subscribe this channel right now. There is a little bit problem with my stylus, so it's creating a little bit problem. Okay, and then we discuss about more about the reactions, and I try to convey my message in a complete proper way. And thank you very much. We will discuss this later. Thank you.